On the morning of 26 January 1700, the Pacific Northwest coast dropped over 2 meters into the ocean in a matter of seconds, sending a silent megathrust tsunami across the Pacific Ocean that battered the eastern shores of Japan hours later without a single local tremor to warn them. Along the modern coastline of British Columbia, Washington, and Oregon, entire stands of Sitka spruce were instantly drowned in salt water, preserved as gray, petrified ghost forests that still stand along tidal estuaries like Niskoan today. Most people look at the Pacific Northwest as a quiet, rain-soaked paradise of evergreen canopies and scenic river valleys, assuming the landscape is a static backdrop to modern infrastructure. But the headline framing that treats this region as merely a green, peaceful corner of North America is fundamentally flawed. What we are actually looking at is a continental subduction engine operating on a loaded, recurring clock, a geological pressure vessel where the Juan de Fuca plate is currently locked beneath the North American plate at a rate of 40 millimeters per year, storing elastic energy along a 1,000-kilometer fault line. The true, far more compelling story is that the modern infrastructure of Western North America, from Vancouver Island down through the Columbia River Basin, sits directly on top of a catastrophic plumbing system shaped by hydraulic violence and volcanic destruction almost beyond human comprehension. Every major feature of this landscape, from the steep basalt cliffs of the Columbia River Gorge to the massive freshwater reservoirs of the Cascade Volcanic Arc, is not a permanent monument, but the recent temporary product of planet-scale physics. Consider the Columbia River system, draining a basin of 668,000 square kilometers, an area larger than the entire country of France. It punches directly through the Cascade Mountains, discharging an average of 7,500 cubic meters of water per second into the Pacific Ocean. During peak spring runoff, that discharge skyrockets past 28,000 cubic meters per second. To understand the sheer scale of hydraulic force required to carve that corridor through solid volcanic rock, one must look back to the end of the last ice age, roughly 15,000 years ago. At the margin of the Cordilleran ice sheet, a massive ice dam holding back glacial Lake Missoula repeatedly ruptured, releasing up to 2,000 cubic kilometers of water in a single catastrophic burst. The resulting megafloods exploded westward with a peak discharge exceeding 17 million cubic meters per second, a rate 10 times the combined flow of every single river on Earth today. The water moved at speeds up to 130 kilometers per hour, stripping bedrock clean, transporting 200-ton boulders over hundreds of kilometers, and carving out the channeled scablands in the Columbia Gorge in a matter of days. This same violent mechanics created Mount Mazama 7,700 years ago. When that stratovolcano erupted, it ejected more than 50 cubic kilometers of magma, causing the mountain peak to collapse inward into an empty subterranean chamber, forming a caldera nearly 10 kilometers wide and 1,200 meters deep. Today, that basin holds Crater Lake, a body of water plunged to a depth of 594 meters, making it the deepest lake in the United States and holding roughly 18.5 billion cubic meters of water without a single inlet or outlet river, fed purely by precipitation. Yet these ancient events are not isolated historical curiosities. They are the baseline mechanics of a subduction zone that remains fully active today. Beneath British Columbia, Washington, and Oregon, the Cascadia Subduction Zone accumulates strain continuously. Geological records show that massive megathrust earthquakes of magnitude 8.7 to 9.2 occur along this margin roughly every 300 to 500 years. It has now been precisely 326 years since the 1700 event. The immediate critical question this entire episode answers is not whether this subduction system will fail again, but how the precise physical mechanisms of deep crustal stress, volcanic plumbing, and coastal subsidence will manifest when the 1,000-kilometer fault line finally releases its stored energy across North America. A faint horizontal line etched 400 meters high into the exposed basalt cliffs above the Columbia River marks a watermark not seen since the Pleistocene epoch, a level where a single ancient flood carried more water than every river on the surface of the Earth combined. For over 10,000 years, the baseline of the Pacific Northwest was defined by this post-glacial stability, creating the illusion of a permanent, predictable landscape. But when modern engineers and geologists began instrumenting this region in the mid-20th century, they mapped a system whose historical baseline was far more dynamic and far more volatile than short-term human memory ever accounted for. Popular narratives often frame places like the Columbia Basin, the Cascade Volcanic Arc, and the high semi-arid plateaus as stable wilderness areas occasionally disturbed by isolated natural disasters. That framing is completely incorrect. The real story, and the far more crucial mechanics to understand, is that this entire terrain is a continuous, interconnected geological archive spanning 35 million years of extreme climate shifts, massive volcanic inundations, and radical hydrological transformations that established the very baseline modern North America relies upon today. To see how far outside the historic normal our current geological epoch rests, one must look at the baseline records established across deep time. In the eastern expanses of the region, ancient soil horizons known as paleosols preserve a 35 million year climatic calendar spanning 1,267 hectares. During the early Cenozoic era, this territory was a warm, humid tropical floodplain, depositing deep red clay layers saturated with iron and oxides. As the regional climate transitioned over millions of years into a cooler, drier steppe environment, the soil composition shifted to limonite yellows, while black lignite veins preserved the compressed carbon of ancient swamps. This historical transition established a critical baseline. The regional environment can shift from tropical rainforest to arid scrubland in geological terms, leaving behind ultrafine clay deposits so sensitive that a single footprint can disrupt the surface for decades. Further south and east, during the Pleistocene epoch between 11,000 and 2 million years ago, the baseline was not defined by desert dust, but by immense inland pluvial seas. Lake Chihuahuan covered more than 1,290 square kilometers, reaching depths exceeding 114 meters. If you stood on the site of modern towns like Paisley today, you would have been submerged under more than 100 meters of standing water. Massive water bodies like Lake Lahontan and Lake Bonneville were so vast they generated their own localized microclimates, mirroring the modern Great Lakes system. The baseline shifted abruptly 10,000 years ago during the Great Drying, when regional evaporation rates permanently outpaced precipitation. As these inland seas vanished, they left behind wave-cut terraces etched 400 feet high on desert ridges, alongside massive alkaline salt flats like the Alvord Desert, 12-kilometer stretches of cracked clay that serve as the chemical footprint of a vanished aquatic world. When modern human development began organizing this landscape, particularly with the construction of 14 major hydroelectric dams on the Columbia River main stem starting in the 1930s, engineers built their infrastructure around the historical river baseline. They mapped a river that dropped nearly 800 meters from its headwaters in the Canadian Rockies down to sea level, tapping into a natural hydraulic engine that today produces roughly 40% of all hydroelectric capacity in the Pacific Northwest. For thousands of years prior, indigenous trade networks operated around Salilos Falls, a permanent trading hub known historically as a central economic engine of the continent. The construction of the Dalles Dam in 1957 submerged those falls under meters of impounded reservoir water, permanently altering the river's flow dynamics and establishing a synthetic baseline for regional power grids, municipal water supplies, and salmon migration routes. Yet, this engineered baseline sits directly within a volcanic arc containing stratovolcanoes like Mount Hood, standing at 3,429 meters elevation, and Mount Meager in British Columbia. When Mount Hood last underwent a major eruptive phase in the late 1700s, it altered regional river channels with massive lahars, volcanic mudflows that displaced millions of tons of sediment. Geologists from Natural Resources Canada and the Canadian Hazards Information Service, alongside international monitoring agencies, have long established that the current baseline of quiet fumarolic emissions, localized hot springs, and subtle hydrothermal circulation is merely an inter-eruptive baseline. The physical infrastructure of Western North America, from transboundary transmission lines to major deepwater ports, was designed during an exceptionally quiet period in this 35 million year history, measuring performance against a century of stability in a system where the true baseline is defined by catastrophic transformation. A single subterranean organism spanning nearly 9 square kilometers beneath the Blue Mountains is quietly fracturing the root systems of an entire forest, consuming living timber from below while remaining completely invisible from the surface. Sensationalized headlines frequently depict these underground phenomena as bizarre, localized mysteries or random ecological anomalies. That loose framing completely misses the underlying physics. The real story, and the precise physical mechanism that demands our attention, is how subsurface biological sprawl, thermal fluid dynamics, and subterranean volcanic plumbing interact to destabilize massive expanses of the Earth's crust across the Pacific Northwest. What is actually happening beneath our feet is a continuous, highly structured engineering process driven by geothermal pressure, chemical weathering, and tectonic stress. To understand the mechanics, consider the subterranean architecture of lava tubes and natural thermal conduits that honeycomb the region beneath volcanic fields like Newberry Volcano, a massive structure whose central caldera spans 8 by 10 kilometers. When molten basaltic lava flows across a landscape, the outer boundary layer cools rapidly upon exposure to the atmosphere, solidifying into a rigid, insulating crust of basalt rock. Inside this hardened sheath, liquid lava continues to stream forward at temperatures exceeding 1,100 degrees Celsius. Once the volcanic supply at the vent exhausts itself, the interior liquid channel drains out under gravity, leaving behind vast hollow conduits, lava tubes like Lava River Cave, that stretch for kilometers beneath the surface. In sub-zero winter conditions, surface runoff drains into these underground passages, where it encounters localized geothermal heat sources powered by magmatic chambers lurking kilometers below. This interaction creates the exact physical mechanism observed at features like Lost Lake near Mount Hood. During wet autumn months, precipitation fills the lake basin normally. But as water levels rise, hydraulic head pressure forces the water downward into submerged lava tube openings functioning as natural geological drain pipes. The lake does not evaporate. It physically drains into the volcanic plumbing network below, feeding regional aquifer systems. Where this groundwater contacts hot, shallow crust near stratovolcanoes like Mount Hood or Mount Meager in British Columbia, the water undergoes superheating under extreme pressure. Because the weight of the overlying rock prevents the water from flashing immediately into steam, it becomes a pressurized, buoyant thermal fluid. When this superheated fluid finds paths of least resistance upward through fractured fault zones, it escapes to the surface as geothermal hot springs, or in extreme cases, causes phreatic and steam-driven explosions. If humans drill directly into these pressurized hydrothermal zones, as occurred at Old Perpetual Geyser, the sudden release of overburdened pressure causes the superheated groundwater to instantly flash into steam, expanding by a factor of 1,600 and propelling violent columns of boiling water into the air at regular intervals. Simultaneously, a massive biological mechanism operates in parallel through the forest floor. The fungal network of Armillaria ostoyae. Sprawling across 880 hectares, an area larger than many urban centers, this single living organism spreads through thread-like subterranean structures called rhizomorphs. These black, root-like tendrils penetrate healthy root systems, secreting enzymes that digest wood tissue and cut off the flow of water and nutrients to the canopy above. The fungal network acts as a slow-motion subterranean excavator, weakening structural timber across entire valleys while drawing energy from decaying organic matter. These interlocking systems, subterranean drainage channels, pressurized hydrothermal conduits, and expansive root-decaying fungal networks, are monitored by array instruments managed by the Canadian Hazards Information Service and the Geological Survey of Canada. Ocean Networks Canada tracks offshore seismic signals along the subduction zone, while terrestrial borehole strain meters and tilt meters record subtle crustal deformation. When localized seismic swarms occur without a single dominant main shock, instruments confirm that magmatic fluids or high-pressure groundwater are migrating through subterranean basalt networks, altering pore pressure along active fault lines and quietly moving the entire region closer to its physical breaking point. An automated alert-ready signal broadcast to mobile phones across coastal British Columbia and the Pacific Northwest gives residents between Tofino and Victoria as little as 15 to 20 minutes to reach high ground before a megathrust tsunami crests over the shore. When sensational media reporting covers Cascadia, it often focuses on cinematic destruction, treating the threat as a distant sci-fi movie scenario. That loose framing severely understates the actual, immediate economic and operational reality. The far more critical story, and the one that directly impacts daily life across Western Canada today, is that our critical infrastructure, transport corridors, and energy grids are already operating within extreme microclimatic and geological pinch points, where a single localized trigger propagates into a multi-billion-dollar regional shutdown. Consider the immediate physical exposure of our transport corridors. The Columbia River Gorge, stretching 130 kilometers and cutting through 4,000-foot vertical basalt cliffs, functions as a high-velocity pressure funnel between cool coastal air and hot interior desert systems. Winds regularly exceed 60 kilometers per hour, creating a natural wind tunnel that dictates regional shipping traffic and commercial barge operations along the main river artery. When extreme atmospheric rivers hit this topography, such as the catastrophic November 2021 event that dropped over 200 millimeters of rain in less than 48 hours, the steep volcanic slopes become saturated beyond their plastic limit. Landslides and debris flows instantly sever rail corridors through mountain passes, cutting off the port of Vancouver from the rest of the Canadian economy and stranding billions of dollars in freight. To understand the scale of vulnerable coastal infrastructure, look at the 580 kilometers of coastal dune systems and jagged headlands. Massive monoliths like Haystack Rock, standing 72 meters above the surf at Cannon Beach, are actually exposed remnants of ancient basaltic lava flows that extended hundreds of kilometers from inland vents millions of years ago. These coastal formations absorb relentless wave energy from the North Pacific, but when a full rupture occurs along the offshore Cascadia Subduction Zone, the coastal landmass drops suddenly by 1 to 2 meters. Saltwater inundates low-lying coastal estuaries, transforming living temperate rainforests into drowned ghost forests of petrified Sitka spruce within hours. Inland, the economic impact shifts from marine inundation to severe hydrological compression. Across the Cascades, a drive of just 2 hours moves a traveler from temperate coastal rainforests, receiving over 2,500 millimeters of annual rainfall, to semi-arid sagebrush basins, where annual precipitation drops below 250 millimeters. The Alvord Desert, a bone-dry 19-kilometer-long playa, regularly experiences summer temperatures exceeding 38 degrees Celsius, creating severe evaporative demands that draw down regional irrigation reservoirs. When dry steppe conditions expand, the Canadian Wildland Fire Information System records rapid fire escalation across timber stands weakened by the armillaria root rot fungus, threatening critical transboundary electrical transmission lines that supply power to millions of residents. Even our iconic visual landscapes conceal massive structural hazards. Mount Hood, towering at 3,429 meters, sits less than 75 kilometers from major urban population centers where over 2 million people live and work. The volcano is active, with its last major eruptive phase in the late 1700s producing pyroclastic flows and massive lahars that choked the Columbia River tributaries with sediment. Near Seattle, the 184-meter Space Needle would be dwarfed by natural vertical features like Multnomah Falls, which plunges 189 meters across 2 distinct basalt steps fed by pressurized underground springs discharging up to 560,000 liters of water per minute. If a volcanic reawakening or severe seismic shift disrupts these underground spring systems, municipal water supplies and hydroelectric intakes across the Pacific Northwest would face immediate contamination and physical structural failure. Public Safety Canada, Emergency Management BC, and the Alberta Emergency Management Agency regularly model these cascading failure modes. When a single major arterial road closes or a primary reservoir intake drops below operational levels, supply chains fail within 72 hours, proving that our modern, highly optimized lifestyle depends entirely on a fragile, temporary alignment of volatile geological forces. 17 distinct seismic stations across Vancouver Island recorded microseismic signals over a 14-hour window, and not one of them registered a distinct primary wave, because there was no sudden fracture, only the slow, continuous grinding of thousands of square kilometers of rock slipping deep beneath the crust. Media outlets often sensationalize these episodes as immediate precursors to catastrophic ruin, or dismiss them entirely as routine background noise. That superficial binary is completely inaccurate. The actual scientific reality and the true boundary between established facts and genuine unresolved mysteries is far more subtle and significantly more unsettling. What we know beyond question is that the subduction geometry, thermal plumbing systems, and massive post-glacial drainage networks of Western North America form a single, fully locked engine. What remains genuinely unresolved by modern geophysics is the exact tipping point where subsurface stress transfer converts deep crustal tremor into full fault rupture. The factual framework is rigorously established. The Juan de Fuca plate is subducting beneath North America at 40 millimeters per year, generating recurring episodic tremor and slip events under Vancouver Island that temporarily redistribute strain onto the locked offshore segment of the Cascadia Subduction Zone. Volcanic centers across the Cascade Arc and the Garibaldi volcanic belt maintain active hydrothermal circulation, while deep basalt lava tubes continuously drain alpine snowmelt into subsurface aquifer networks. Yet, despite advanced instrument arrays deployed by Ocean Networks Canada, Natural Resources Canada, and the Canadian Hazards Information Service, scientists cannot predict precisely which microseismic swarm will trigger a full rupture along the 1,000-kilometer fault line, or when a shallow magma chamber beneath stratovolcanoes like Mount Hood or Mount Meager will breach its upper host rock. To monitor this evolving hazard, there are 3 specific checkable parameters on the watch list that will tell us which way this system is moving. First, watch for an increase in the frequency and shallowing depth of seismic swarms detected along the Leech River Fault or near major volcanic edifices, moving from depths of 25 kilometers up toward the upper 5 kilometers of the crust. Second, monitor whether Natural Resources Canada or provincial emergency management bodies issue formal advisories regarding accelerated uplift rates measured by high-precision continuous GPS stations along the western coast of Vancouver Island. Third, track real-time geochemical and temperature changes in thermal springs surrounding Mount Hood, Mount Cayley, and Mount Meager, where elevated carbon dioxide degassing and sudden temperature spikes indicate fresh magmatic intrusion into shallow plumbing channels. Until one of those 3 specific indicators occurs, the situation is best understood not as an imminent catastrophe, but as an active, highly strain-loaded tectonic margin operating precisely within its historical interseismic interval. The modern infrastructure of North America was built during a momentary pause in a 35-million-year history of extreme geological violence, and the Earth beneath us is simply waiting for the clock to run out. Let us know in the comments below what city or region you are watching from today. Subscribe to stay informed as we track the real-time mechanics reshaping our living planet.